So the first thing we're going to talk about are our medical gases. We're going to talk about some of our gas mixtures. First part of this, just some philosophy to go along with the way I'm teaching. So the first thing is, relax, have a good time where you're learning this, and make sure you keep coming to class. It's always helpful. And one of the things, and I think sometimes we forget this, is you're never going to get new results if you continue repeating old habits. We have a tendency to be comfortable with the things that we have that we do, and then we kind of wonder why we're not getting forward or why we're getting some of the same results. And so what we need to do is stop and look and say, perhaps it's time to make some changes and to get rid of some of those habits. What are we going to study? We're going to look at Egan's chapters 40 and 41. There's going to be parts of the workbook that I'm going to assign to you out of chapters 40 and 41 within the workbook. I don't have any at this particular point, but I'm going to get those posted for you. Additionally, we're going to use chapters 1 and 2 in White's equipment book. That's the hardback. There's 30 questions at the end of each of those chapters. You will be responsible to make sure that those do get done and get turned in. Now, I will tell you this, there are some wrong answers in those questions and in the back of the book. So if you just decide to copy down the answers and not have to worry about reading the questions or anything, you will get some of them wrong. If there is a wrong answer and you know what the right answer is, write it in and I will take it, okay? And then we're going to look at chapters 11, 12, and 13 in White's Basic Clinical Lab Competencies. This is your softback book, and those are only 10 questions at the end of those chapters. So the bottom line to all of this is basically how hard you're going to work. All of you at this particular point have 100 in this class. Well, that's the part. And that's simply because you're starting the class and you're going to do well. So things we do, there's your attendance assignments. Most of those will be done at the end of the day. You're going to have other classwork and outside assignments. There are quizzes, and there is a final assessment. And as we get through the course and we get closer to the end, I will give you that final assessment. So when we talk about medical gases, one of the questions people ask is, well, what's a medical gas? Well, a medical gas is a gas that's been purified. The Food and Drug Administration, FDA, is the one who handles medical gases. It puts out a document called Fresh Air. It tells the manufacturers how to make sure that their medical gases are pure. They also do investigations and they do checks on the different manufacturers to make sure they're doing what they're appropriate at that point. They tell them how to handle their cylinders, take care of their cylinders, and then they always want to investigate anything that may go wrong at this particular point in time. So there's many grades of commercially produced gases. One time, when we were in the older building, you could actually go to the 7-Eleven at that particular point and buy little canisters of flavored oxygen if you were kind of interested in it. I guess you can also go, from what I hear from some of the students, you can go to Vegas and pick up some oxygen if you have a headache, and that's going to help you a little bit too. So our medical gases are 99% pure. The nice thing about oxygen is actually 99.5% pure, so it meets the medical gas standards. Gases do have fire risks. Sometimes they burn, sometimes they don't burn, but they do help burn occurring, and sometimes they are not flammable. They don't burn at all. Oxygen happens to be one of the non-flammable support combustion gases. If you're out there on a weekend and you want to barbecue, but you just can't get the fire going, borrow Grandpa's oxygen, put it next to the fire, and I'm sure it'll start at that particular point. The only thing is be extremely careful when you do that. You don't want to blow yourself up. So the number one cause of fire deaths is smoking, and this has been going on for years and years and years. And what's interesting, in 2015, there was a presentation, and you'll see it coming up on the slides. There was a presentation that was made about how do we stop people from smoking, or how do we treat people who we know are still smoking. And the question came down to, Do you treat them knowing that they're going to smoke and you're going to hopefully prolong their life? Or do you not treat them knowing that their lives are going to be shortened a bit? And we still haven't come up with an answer on that one. So this came from the National Fire Protection Agency Journal, February 2009, and it tells you that the dangers of people who smoke. People who live in apartments will sometimes burn the entire apartment down. In some cases, if they're living in a home, they may burn the home down also. This is what a cylinder looks like after it has blown apart. Okay. And this is one person's fire lesson. As you can see, he was smoking while he was cooking meth, and he actually burned his home down. The moral of the story is if you decide that you want to do meth, don't be cooking while you're smoking. So there's three different uses for our gases. One is your laboratory gas. You guys, I'm sure, have talked about PFTs. I know you've talked about the ABGs. In those labs, we use medical gases. And so those are some of the places that you will see these, sometimes the first places. There's also the anesthetic gases. These are the ones being used in the operating room or in the operating center, because you guys know that there's standalone outpatient operating centers, and they're also using these gases. And then the last one, these are the ones we deliver. These are your therapy gases. They include your oxygen, your medical air, your heliox, your carbogen, nitric oxide, different things along that line. So these are the gases we're going to talk about. When we're talking about gases, we're going to measure their pressure, and we need to know what the pressure of the gases are because of how the gases are delivered to our patients, okay? And you remember, and I'm sure you remember this from Sam, temperature and pressure change the basic characteristics of a gas. If you heat a gas, you have more molecular movement, and with more molecular movement, you have a higher pressure. When you cool that gas, what's going to happen is the movement slows down, and as a result of that, the pressure also changes. When we talk about our gases are dry. One of the formulas we're going to talk about today is one that you've also talked about with David, and this is your alveolar air equation. When we're looking for the amount of oxygen in the alveoli, we have to take out the 47 millimeters of mercury that is the water vapor pressure. Otherwise, we're going to get an incorrect answer because water vapor pressure exerts its own pressure, okay? So when we're delivering oxygen or delivering any gases to a patient, that gas is dry, and as a result of that, our patients will sometimes end up with stuffy noses, they'll end up with nosebleeds, very uncomfortable, and when that happens, we need to make sure that we're watching those patients and trying to give them some humidity or something else along that line. So oxygen is our first gas we're going to talk about. That's simply because it's the most important gas for life. Oxygen is a drug, and because it's a drug, it has to have a physician's order. Now, one place, if you ever are around cylinders, medical gas cylinders, you notice that there's a tag on there, and that tag will tell rescue folks that they can use oxygen, and they can apply as much oxygen as they need to. And when they're taking a patient to the hospital, they're talking to a physician, they're telling them what they're doing. A physician can tell them to, keep the oxygen on, do what they need to. When they get into the hospital and we start to take care of them, then that oxygen has to be ordered, okay? One of the things, and this is part of the reason why you take patient assessment, is because in order to take care of our patients who are on oxygen, we have to be able to monitor them. Too much oxygen, too little oxygen, not a good thing. It can either cause some major issues, and we'll talk about those, or it's going to cause a major issue that's not going to have a very happy outcome to it. So we need to make sure that we practice our patient assessment skills. It requires monitoring. We're going to talk about our pulse oximetries. You guys are doing ABGs at this particular point in time, and because you're doing that, that's another way for us to go ahead and monitor the outcome of the oxygen and make sure it's working as it needs to. It is the star of the show. So just a little history. I'm not going to go into a whole lot of it, but we really didn't know per se what oxygen was the way we recognize it today. But the Chinese, the Greeks were people, they knew that there had to be something in the air that was going to allow us to live. Leonardo da Vinci is another one, and he said, same thing. There's something going on here. We need to figure out what it is. Robert Boyle, you guys remember him. He said combustion, a flame, respiration. You have to have something. And it's going to be the same thing if it's the flame or us breathing at this particular point. The barometer actually came into about in the 1660s, and this was Torricelli and Pascal. They developed it. And basically, when they did this, they used mercury. So guess what? We measure our barometric pressure in millimeters of mercury. You can also measure it in centimeters of water. And when we talk about that, we see that sometimes when we're using our ventilators and things along that line, when we're doing some of our cuff pressures, when you get into critical care. So we're able to use either the millimeters of mercury or the centimeters of water pressure. 1 millimeter of mercury is equal to 1.36 centimeters of water. So in 1670, Robert Boyle and Robert Hooke got together, and when they did is they figured out the respiratory movement was how you got oxygen into your lungs. And then in 1700s, as you can see, this is Carl Scheele. He was a pharmacist. He was really interested in the gas mixtures and everything. He generated, as you can see, oxygen. He called it fire air. He had a somewhat shortened life, and part of the reason he had that shortened life is because he used to generate toxic gas substances also. 1774, Joseph Priestley was credited with discovering oxygen. And if you notice, we don't call it defossilicated air. I think the patients would probably run out of the room if you told them that's what you were giving it to them. He was credited with discovering the oxygen, as I said. They went back and found out that Bergman actually published Scheele's discovery in 1774. Did it make a difference? No. Priestley is still the person who gets the credit for discovering oxygen. Now, one thing about Priestley, and you'll read this when you read the supplemental information, he was a Quaker. He was not a very good neighbor, by the way, but he's the one who came up with carbonated water. So if you drink soda or anything that has carbonation in it, he's the one who found that for you. Antoine Lavoisier was another one. He published his discovery of oxygen. He was a scientist, but his main job was a businessman. And unfortunately, his business is what got him guillotined. 1790, here's Thomas Beddoes and J. Watt. These guys came up and said, we can use oxygen and we can use it for anything. And they started the Pneumatic Institute in Bristol, England, and that lasted for a couple of years. Probably the one thing that got them in trouble is using it for the anything. At this point in time, we didn't realize that there were negative effects to giving too much oxygen because we really didn't understand that much about it. But these were the first guys who actually used it for us. In 1868, Barth actually came up with the first cylinder. And the first cylinder allowed, as you can see, to store the gas and then bring it around and be used. He also rented the equipment, and I'm going to show you an old article in the newspaper that talked about it. So he was really our first gas distributor, if you think about it. And there it is, George Barth, and he's talking about how safe oxygen is and how you can rent it. 1800s, 1900s, we started to come up with our first medical gas devices. Most of these were based on the anesthesiast devices at this particular point. We, as therapists, are very closely related with the anesthesia community. These guys do a lot of our signing offs, if we're doing art lines or intubations and things like that. They're also involved with the curriculum of your program. So in 1907, Sir Lane came up and he got the first nasal cannula. I'll show you that in a minute. They used oxygen to treat the sick children and adults of the World War I gas poisoning. And finally, in the 1900s, we began to realize there's some negative aspects from having too much oxygen. And this is where we started to realize that we had to be a little bit more conscious and aware of what we were doing at this particular point. So here's an early nasal cannula. Looks like it has some metal to it. Probably this was not something that you wanted to wear outside on a rainy or snowy day. And then this was called a continuous recording of blood oxygen tensions by polography. This is the article that Leland Clark actually. Anyways, Dr. Leland Clark is the one who came up with the Clark electrode. I'm sure probably Juice has mentioned to you, these electrodes are found in our ABG machines. Really revolutionized our business, made it much easier for us to go ahead and to figure out what's going on with our patients' P-little-a-O2 at this particular point. He also, by the way, in case it's interesting to know, is that he came up with the glucometer, which is used to measure your blood glucose levels. So he was pretty good at that point. He actually was up in Ohio State. What we see also is the Severnhouse is another electrode. This is the PCO2 electrode. The SANS is the pH electrode. Severnhouse is really a modified pH electrode. And you're going to talk about those in classes as they come up later also. So some terminology that you have seen. A big P is always pressure, in this case, either millimeters of mercury or centimeters of water. I is going to be your inspired, and it could be any of the gases. And so where you see O2, etc., it's going to be, for example, P, big I, O2 is the partial pressure of inspired oxygen. F is fractional. We use that when we talk about the oxygen we're delivering to our patients. PB is barometric pressure. Remember, at sea level, it's 760 millimeters of mercury. Here in Tucson, anywhere from 698, 713. It changes in other parts of the state also. Big A always is alveolar. C is going to be the content formulas. V is venous. If it's a V with a line on top of it, it's a true mixed venous. And the only place you can get a true mixed venous blood gas is out the pulmonary artery. And then little a is always arterial. So one of the things when we talk about oxygen, it is colorless, odorless, tasteless. You can see through it. If you stop and think about it, if there was a haze to oxygen all the time, then we'd have to get used to looking through haziness. When it's windy outside or when it was smoking, you know, the mountains were on fire at that particular point. There was some haze out there, and we had to get used to looking and dealing with that. It can be gas, liquid, or solid. It is paramagnetic, which allows it to attract other gases to it. It's a free radical in nature, and the free radical of oxygen is ozone, and it's O3. And when we talk about too much oxygen, we're going to talk about the overproduction of ozone molecules in the body. This is not a good thing since it really affects the nervous system, and we have some issues that go with that also. It also has a tendency to really affect the lungs and a person's ability to breathe. Most of the organisms do use oxygen. Remember, your anaerobes don't. We can use oxygen on bacteria that are anaerobics and kill them because the oxygen will take care of that for us. It makes up approximately 50% of the Earth's crust. We find it in water, on almost everything we do, and it's the third most abundant element in the universe behind hydrogen and helium. Extremely active. Fortunately, it's not so active that it's going to knock us around the parking lot or anything like that. Doesn't want to combine with inert gases, but we make it. We're going to talk about heliox, and we're going to talk about how do we get it to combine with heliox. It's a poor conductor of heat and electricity, and as I mentioned before, it doesn't burn, but it sure supports combustion, and that's where we get a higher, faster fire for our patient, for not our patients, for people. The STPD of it is 1.429 grams per liter. It's denser than medical air. Denser, as you guys know, means heavier. And I'm going to show you why that's important, or tell you why in just a minute why that's important. The partial pressure will decrease with altitude. It increases with altitude, okay? As you go up the mountain, the partial pressure of oxygen goes down. As you go into Death Valley, the partial pressure of the oxygen becomes much greater. We also, if you're a scuba diver or something like that, you know that when you dive, you have to dive without 21% oxygen because you're getting too much oxygen in your lungs at that particular point in time. One of the problems we have, people have a tendency of forgetting, if you go to, and Denver's a good place to pick on, Denver, its barometric pressure is right around 600 millimeters of mercury. If you leave Tucson and go to Denver and you're going to go hiking the mountains, one of the things you don't want to do is go hiking the mountains the day that you arrive. You've got to acclimate yourself to the new partial pressure of oxygen. If you were to try to do that, go ahead and hike that mountain on that first day. If you weren't really careful or you went too high, you could end up with a fatal form of pulmonary edema, which unfortunately, fatal probably is the operative word at that particular point. So to determine the partial pressure of oxygen, there's your Dalton's formula. So I'm going to tell you who it comes from. PB times FiO2. Because we're measuring the partial pressure of oxygen in the surrounding or ambient air, we don't have to remove the water vapor pressure. That vapor pressure is part of what's being exerted upon our body. When we're talking about what's in our lungs, though, we have to remove that 47 because otherwise it's going to give us too high a partial pressure of available oxygen that's going to diffuse from the lungs into the arteries. So when you're reading questions on this, you need to know, am I outside? Am I mountain climbing? What am I doing? If I am, I'm going to leave that 47 millimeters of mercury in there. If I'm talking about in the body and I now want to know what's available for diffusion, I have to take that 47 millimeters of mercury off of the barometric pressure. So as we said, it exists, gas, solid, or liquid. Compressed gas is really, really, really cold. And how do we know this? Because people have messed with compressed gas. When we talk about cylinders, we have an opportunity to get into the lab. When we start using our cylinders, if you go over and touch them, the cylinders are very, very cold. And if you feel the regulators reducing valves, they're very, very cold. And that's because we're using this gas, okay? And that goes with one of your laws that you learned. Good question. Think about which one you think it is. Where does it come from? You remember in high school we talked about photosynthesis. We're going to go ahead and get oxygen from the plants and the trees around us. We can electrocute water, which is not probably a good thing. You don't want to be in the water when that happens. There's sodium chloride decomposition. It doesn't really produce a whole lot. It gives us enough for photosynthesis to be able to live. However, it's not going to give us what we need to be able to take care of our patients. We have concentrators. If some of you guys have family members or know somebody who has oxygen with them all the time, we have concentrators that are in the home. We have concentrators that people are able to carry with them now. There's very small ones that they can just put on their shoulder and go wherever they want to. And this has really been good for them because they can take them if they want to exercise. They can take them on flights. If they're flying somewhere, going on a trip on a boat or something or on a ship, they can take those with them too. Main ones, we still have the semi-permeable plastic membranes. The main one, though, is the molecular sieve. What you have to remember with the molecular sieve concentrator is this. You need to stay what is ordered for you. And the reason is, as you increase the amount of oxygen that you want your concentrator to deliver to you, the actual FiO2 begins to decrease. So at 2 liters, you're getting somewhere around 95% oxygen, which is beautiful. At 5 liters, you may be down in the high 80s. They've gotten a little bit better, but they still have that decrease at that point. And so when we're dealing with our patients, we always need to remind them, do not change your liter flow on your concentrator, because if you do, you're actually getting less oxygen than you would otherwise. Semi-permeable plastic membranes, 40% FiO2, didn't matter what you did, you always had 40% FiO2, okay? But the concentrator is the most cost-effective home care oxygen delivery device. People with concentrators, though, you're going to find out, do have cylinder backups just in case they need them, okay? For the hospital setting, we're looking at fractional distillation. Very common, very economical. Not only do we produce oxygen, but we produce some of our other medical gases from this also. When we talk about fractional distillation, if you like watching old movies, especially old westerns, things like that, you'll see these people, they're out there making moonshine. How are they making their moonshine? They're doing with fractional distillation. So if you're interested, just watch an old movie. It has a distilling tower. You're going to filter your air. Guess where the air is coming from? And all of you who said the ambient air around you, that's exactly where it's coming from. But we're going to go ahead and filter it, remove water, CO2, whatever else we need to. It would be nice to tell you that we're going to remove 100% of the water in the surrounding air. We don't. And one thing you're going to see is that we have filters. We have filters on our equipment. We have filters in the lines the piping system that we use to put the oxygen through also. We're going to go ahead and compress the gas, it cools it, or actually warms it up, and then we're going to cool it by expanding it rapidly. This is called the Joule-Thomson effect, and then we're going to slowly heat it again. And when we do, at the various temperatures, this is where the other gases will start to rain off, if you want to think about it that way, or boil off, and we'll collect those and use those as we need to. So this is your memorization for today. Okay, not really, but this will show you basically what a fractional distillation tower looks like. Okay, so the next gas we're going to talk about is medical air. And sometimes people will ask, well, why do you use medical air? Well, not everybody who comes in the hospital needs oxygen. We have patients who have trachs. They bypass their upper airway. They're not getting the moisture or humidity they need to keep their secretions moving. And sometimes we need to deliver moisture to them, and we can use medical air to do that. Plus, about 90% of the treatments that we give our patients in the hospital are off of medical air. So medical air really has a number of different purposes for us. So medical air, as you can see, very much like oxygen, colorless, odorless, transparent. It occurs. You're breathing medical air right now. The only difference is it is not purified, and it's not 99% pure, okay? Standard density, 1.29, much less than oxygen, okay? If you ever get around to measuring specific gravities, this is actually what you want, okay? It's produced by filtering, compressing atmospheric air. We store it. How do we make it? We make it with compressors, okay? Concentrators make oxygen, compressors make medical air. The most common one we use in the hospital is the piston compressor. It works very well for us. For the medical use, it's got to be dry. We're going to cool the gas, produce condensation. Remember, though, we don't get 100% of the water out. We have filters that will take care of that for us. It has to be free of any oil or particulate contamination. They use Teflon rings so that we don't have friction that's going on at this particular point. And it has to give us, as you can see, 100 liters per minute at 50 psi. And the question is why 50 psi? And the answer is 50 psi is the working pressure of our equipment. Now that's a pretty nice thing to know and something you need to remember, because when we start talking about equipment, we have to know that we have to have a 50 psi outlet source to be able to use our equipment and use the gases that we have. Anesthesia's working pressure is around 60 psi. So we're not going to hook our stuff into their equipment because it's way too much for them. It's not going to work like it needs to. So we need to make sure that we understand that ours is 50 psi. For home use, you have the diaphragm compressor. We use this for nebulizers. There's not enough pressure in these to be able to really power our equipment. They're more for breathing treatments and things along that line. And you also have the centrifugal compressor in some cases. Okay, so I'm going to take a little trip back a little bit. One of the things we talked about with medical air is it's got a lighter density than oxygen. And the question is, well, what does this really mean? And basically it means this. If you have a patient, and a lot of times we see with the babies where you're laying them down and you're delivering oxygen to them, as that oxygen is being delivered, the gases are going to start to layer out. And when they do, the oxygen is going to fall closer to the baby and the medical air will be higher. We use an analyzer next to the baby's head so that we know exactly what the FiO2 percentage is for that baby. If we didn't do that and we turned up the oxygen, we're going to give the baby too much. We don't have to turn up the oxygen to give the baby too much. And the reason that we don't have to do that is because the oxygen is falling out around the baby. So it's important for us to understand different densities and the reasons why we do that. Okay. So the next gas, we don't use this one as much. This is carbon dioxide. The reason I'm showing this to you is that because of the carbon footprint and the things that you hear about climate changes, we've gone from 0.03% of CO2 in the atmosphere to 0.04% of CO2 in the atmosphere. Interesting thing about it, when you have carbon dioxide, it hangs around, and they'll tell you it can go anywhere from 300 to 1,000 years before you ever get rid of it. Some of the other gases go away much, much quicker. It too is colorless, odorless, and tasteless, and if you look at this, this is a heavy gas, okay? It does not support combustion. It does not support animal life. It still is pure. We don't use it as much as we used to, but we do use it in our laboratory settings. We use it in our PFT machines. We use it with our ABG machines. And they use it in the heart-lung bypass machines. We also need to know that we can blow off CO2 or we can allow CO2 to build up. If a patient has a a brain bleed of some sort, and we're trying to control that brain bleed, we're going to hyperventilate that patient. Because when you hyperventilate a patient and they're blowing off their CO2, we're going to get some vasoconstriction. We don't want to do it so much that we clamp the vessel down, but we need to do it enough to get the vessel to close down and stop some of that bleeding. If we stop that and we stop hyperventilating them, then we're going to get the vasodilation. So we have to be aware of that when we're dealing with our patients. How long can we hyperventilate a patient before we run into problems? Normally about 48 hours is good. After about 48 hours, the body recognizes there's something going on with that CO2, and it's going to want to go in there and put the CO2 back to where the CO2 needs to be. So we have to be aware of that. We have to be on top of it. If we are going to use it, it has to be mixed with oxygen. And this is your carbogen, okay? You either use 5% or 10%. And we once used it to treat singulitis, which is really a sad disease state. You may want to look that one up. This is interesting. And in atelectasis too. They are still using this for cancerous tumors because they're making it, the tumor more responsive to radiation. Interesting, I was looking the other night, and there's a bunch of articles that say, yes, this in fact is what's going on. But there's also some articles that are sitting here going, yes, this is what's going on. But after a certain point in time, it stops working. And when it stops working, then we lose that advantage that we had with the radiation. So really, it has very, very limited use, unfortunately, at this point. But you see, there it is, the heart-lung machine, your blood gas analyzers. We can use it to regulate some vascular pressures in patients. Most of the time, though, it's going to be diagnostic and in the labs. Helium's interesting. I put a little video online. It's kind of an interesting one. It comes from England. And one of the things that the person who's talking about, when you listen to him, talks about is we could run out of helium. Helium is something that's, if we're going to get it from the earth, we get it from our natural gas wells. There's not that many of them right now. But anyways, like I said, there is a real possibility that we may end up running out of helium. And we're kind of hoping not at this particular point. So there it is, a little bit lighter than everything else except for hydrogen. Very low standard temperature pressure density at this particular point. Does not support life, a good conductor of heat, sound, electricity. Doesn't like to mix with water, doesn't like to mix with oxygen. But we're going to make it do that. So there it is. When we use it, the major two that we use are the 70-30 or the 80-20 mixture. And it's 70 or 80% of helium mixed with 20 or 30% of oxygen. Then when we're using this mixtures or using these mixtures, we do have regulators that are calibrated for helium or heliox, except most of the time we're doing this, we're actually going to use an oxygen regulator and an oxygen flow meter. And I'm going to tell you what we need to do in order to be able to make sure we're delivering the right flow to our patients, okay? This is used to bypass severe cases of large upper airway obstructions. Because the helium density is so low, it's actually pulling the oxygen past that obstruction and getting into the lungs. And as a result of that, it's decreasing the work of breathing. The problem with this, though, is it's too light and it doesn't allow the patient to cough. It's not, or they can cough, but it's not going to make them cough. So there's some issues with it for that aspect. But in order to make sure this patient has some oxygen, it's really, really good to be able to do that. When we administer it, we want it in a closed system. We don't want to entrain outside air. What's interesting, when they came up with the high flow nasal cannulas, they did some studies on that, and they found out because of the flow we get with the high flow nasal cannulas, we can actually deliver heliox quite well. So it's a pretty good, almost closed system for you too. And there it is, and we're using the oxygen flow meter, regulators, whatever. We have to adjust for the lighter density. Each piece of equipment is calibrated for the gas that's going to be run through it. And like I said, we do have some for Heliox. They're extremely expensive. A lot of times they end up at the swap meet or places like that. So much better for us to go ahead and use the oxygen flow meter at that point. So the calibration or the correction factor, you're going to see it called for 80-20 mixture is 1.8. For 70%, it's 1.6. So we can determine total flow we're delivering to the patient. Whenever you see total flow, we're trying to figure out how much gas is that patient actually receiving. And so in order to do it, say for example, here's a little problem and you have some of these on your attendance assignment. If your flow meter is set at 10 liters, your physician says, what total flow is your patient receiving? It's an 80-20 mixture. The correction or calibration factor is 1.8. 10 times 1.8, 18 liters per minute is the total flow of gas that that patient, in fact, is receiving. If the physician says, oh, no, that's way too much. I don't want this patient getting anything over 15 liters, and we're going to change the mixture from 80-20 to 70-30, now we need to know how do we want to set up this flow meter. And basically remember that calibration correction factor is 1.6. And so we're going to say, what is the maximum flow you want? 15 liters. 15 divided by that calibration correction factor tells us that it's 9.4 liters per minute. We're not going to set up the 0.4. We're actually going to go ahead and set the flow meter at 9 liters. Patient's going to get what the physician wants. And I don't know if any of you guys have been to the dentist and they wanted to do some dental work. They can give you nitrous oxide, which is also called laughing gas. It's an anesthetic gas, also like an anesthesia, but it's a very poor one. It has to actually be mixed with other anesthetic gases. The unfortunate thing about this one, it has some forms of neuropathy, increased fetal disorders, spontaneous abortions if you have too much. If you're working around nitrous oxide, you have to wear a monitor. You'll see the folks in the X-ray department, they have monitors to monitor X-rays. People working around nitrous also have to have a monitor to see how much they have too. This one though, if you get a spill, you can actually smell it and taste it. And that tells you that you have to vacate that place. You can't stay in there. It does support combustion and not life. Nitric oxide is another thing you'll hear about. It's often called INO, inhaled nitric oxide. It is colorless, non-flammable. It does support combustion. It is basically smog. This is what's coming out of your vehicle's exhaust pipes. It is a strong respiratory irritant. So in parts of California, when there's no movement of the air, if you've been in Alaska on occasions, you'll have the inversion layer, and they tell you to stay in if you have breathing issues because it's not good for you. It can cause chemical pneumonitis, a fatal form of pulmonary edema. What we see with the patients that we deliver it to is methemoglobinemia and hypoxia. Methemoglobinemia is a result because what NO does, it goes ahead and it stabilizes the ferrous ion to ferric. And when it does, then it can't carry oxygen. It's interesting if you're going to do an ABG on a patient that we suspect this with, the blood comes out chocolate or rust color, and we know for a fact that that's what that patient has. And then what we have to do with this is we have to go ahead and we have to titrate it off of the patient. You just cannot turn it off, because if you turn it off, you're going to get what they call a rebound effect, which means we're going to go back to what why we were treating this patient, and then we're going to get actually a worse outcome with it also. So we have to titrate it off. And so these patients have to be constantly monitored to make sure that we're not seeing the methemoglobin. So what's it approved for? Treatment of near-term infants for hypoxic respiratory failure, pulmonary vasodilation, people who have what we call persistent pulmonary hypertension, PPH. This is when their vessels go into massive vasoconstriction. We can give it to them. It does help relax it. The unfortunate part is it really hasn't changed mortality rates, okay? Now, one thing too, and people will ask you sometimes, especially if you have a bodybuilder, well, I take nitric oxide, why doesn't it affect me? That's because it's not being delivered to your lungs, okay? It's when it leaves the alveoli and it goes through the capillaries and enters the blood system that we start to see problems with it. The other thing you need to be aware of is that you have to have nitric oxide in your body because it allows you to have vasodilation, okay? So we have it within our body. Where the problem comes is adding more to it, and that's where we start to see the problem with it.